Hi, we're Team W, and we're covering ocean tidal power. I'm Will Billini.
Gabriel Lopez.
Joe Hernandez.
And I'm Nikhil Mohip. Today we will be covering the general understanding and background of ocean tidal power. Current designs of ocean tidal power include tidal stream generators, barrages, and tidal lagoons. A possible future development would be dynamic tidal power, which we would hope to improve upon.
History of tidal energy. According to archaeological evidence, people have been using ocean tidal energy for about 400 years. During the Middle Ages, people in several parts of Europe would use tide mills to grind grains such as rice in order to make flour. It is estimated that at one time there were about 750 of these tide mills along the shoreline of the Atlantic Ocean. This includes over 300 of them in North America, 200 in the British Isles, and over 100 in France. However, only about 23 of them still exist today, and out of those 23, only about 10 of them still work without electric power.
Hi, I'm going to talk about tidal stream generators. Tidal stream generators are installed in tidal streams. Basically, they utilize fast-flowing water in tidal streams to move the propellers of the turbines. They operate much like windmills, except that the fluid used to turn the generator is water instead of air. The most common configuration are axial turbines. As you can see illustrated here, these are turbines that are mounted directly into the ocean floor in different configurations. And on the pile is the actual generator with a turbine in front. The first successful commercial installation is in Strangford Lough in Northern Ireland. It is installed in a tidal stream, and as you can see, it's in actual configuration with two propellers on each side of the main post. The environmental impact of this type of a tidal power generator is that marine life can impact the blades or become entangled in them. Another consideration is noise pollution, as the noise from the turbines propagate longer distances and can hamper marine life communication. Another form of tidal power generation is tidal barrages. Tidal barrages operate similar to freshwater dams. The way they work is that water accumulates on one side of a dam-like structure, and when the tide flows in, it accumulates on one side, and then these gates that are known as sluices close. As the tide is flowing out of the basin, the difference in elevation causes an increased head pressure on one side, and then the water flows through the turbines, turning the generator. This is the oldest form of tidal generation. In 1966, the first tidal barrage for commercial use was built in the Reims Tidal Power Station in France. Versus the previous form of tidal power generation, the environmental impact is that silt accumulates in the tidal basin, covering the plant life in the bottom of the seafloor. Also, it reduces the salinity because there is less water transferring from both sides, and that affects the marine life. And also, it impedes the mobility of marine life from one side to the other.
Here's a future design. Dynamic tidal power is a concept invented and patented in 1997 by Dutch coastal engineers Kees Holzenbergen and Rob Stein. With this design, 8 leading Dutch companies experienced in hydraulic engineering and sustainable energy formed a group known as Partners Offering a Water Energy Revolution and designed the following concept. Dynamic tidal power uses large-scale tidal flow to generate electricity. A long seawall of at least 30 kilometers runs perpendicular to restrict tidal flow and create different heights of water on either side of the wall. The T-shape at the far end amplifies the hydraulic head difference. The different hydraulic heads induce a variance in pressure through the narrow tunnels that house the turbines. A pressure difference causes the water to flow rapidly through the turbines to make them spin and generate electric power.
What makes the production of such a high level of energy possible is the highly advanced turbines that were designed specifically to work with an extremely low head. These turbines are bidirectional and they have a peak output of 5 megawatts each. A dam of 40 kilometers in length can accommodate about 2,000 turbines. This would generate over 10 gigawatts of power, which is enough to supply millions of houses with sustainable energy.
Here's an improvement on the current ocean tidal power concept proposed by the power group. Their future design incorporates a T-shaped structure shown here on the bottom left. When the high tide flows into the structure from the left, the tidal energy is concentrated and causes the water to rise. We decided to vary one parameter to understand its effects on hydraulic head difference and hopefully improve on the design, keeping all other variables constant, including water velocity, input and output conditions, length of the dam, and tunnel diameter. In order to store tidal energy better, we changed the geometric structure as shown on the right. To compare the two concepts, we chose to measure the total average surface pressure on the top water surface. The two graphs on top show this correlation. The total average pressure measured for the T-shaped design was about 531 kilopascal. The total average pressure for our curved design increased to about 2300 kilopascal. This shows that our design increased the average surface pressure to about 4 times that of the T-shaped design. The average top surface pressure can be directly related to the hydraulic head of the high tide portion of the structure. By increasing this hydraulic head, we're able to increase the pressure variance through the tunnels, which in turn generates more energy.
In conclusion, we've seen throughout history people have used the power of moving water to facilitate their lives. We now know ocean tidal energy is a clean and renewable source of electricity which reduces the carbon footprint of this technology. Tidal lagoons, barrages, and tidal stream generators all produce electricity now, but many cause environmental issues. We decided to alter the design of dynamic tidal power, and according to our study, changing the T-shaped structure to a U-shaped structure in dynamic tidal power greatly varied the hydraulic head difference. This leads us to believe it would create more energy. Thank you.